All right, good morning. Let's see if this goes. Okay, perfect. Yeah, good morning. So I'm going to be talking about some research I did last fall, mostly in October, that led to the discovery of a few vulnerabilities, primarily focusing on an unauthenticated remote code execution in the Windows networking stack. But before getting into the good stuff, I'll do a little bit about me. So I've been in the computer security field for coming up on 20 years now, most of that doing offensive research and development. But about 3 years ago, I joined Field Effect and switched to the defensive side, mostly working on our EDR driver, doing Windows kernel development. But still working on that requires some OS internals knowledge. And occasionally I get sidetracked and start looking for bugs, which kind of led to this talk. So why am I giving this talk? So big software systems, like especially closed source systems, can be intimidating to reverse engineer. So in the past, I've looked into larger projects where I thought there would be nothing to find, but it turns out there was a lot of low-hanging fruit. So I think people are either intimidated or they assume that the stuff has been looked at, and so no one's taking a look at some of these things. So hoping to share some tips on my approach and kind of help other people out that are wanting to reverse engineer kind of bigger things. And the goal when you're looking at something from looking for bugs anyway, is you don't need to find all the bugs in the system, but you're looking to find just a few good ones is all you need to have it considered be successful. And also along the way, doing all this research, I ended up learning probably more than I needed to about the Windows networking internals, so thought sharing some of that knowledge would be good. And yeah, the other reason we do it is like reverse engineering, finding bugs, trying to figure out how to take over someone else's program. It's fun, right? We don't all do this just because it pays the bills, but also it's enjoyable. And last but not least, I've always heard good things about REcon and never been, wanted to come, and no one told me that I didn't have to give a talk to come. Okay, so I'm going to be going over some of the things that I think about while looking for bugs in kind of systems, and usually how I approach a complicated reverse engineering task. So just to start, we're good. Just talking in general about bug hunting and how I think about things. So looking for software vulnerabilities is a bit of a gamble. All sufficiently large software is going to have bugs, but to be able to find them, you have to make sure you're looking in the right places, and also know how to spot the mistakes. So knowing the different types of bug classes that could be there and what they would look like in the code is important. And so your goal when spending time doing research is you're not guaranteed of finding anything, but you want to try and maximize your chances of success by looking in the best areas and kind of making the best use of your time. And so having a good understanding of any system is always going to increase your odds. So basically, the more you know about how something like the network stack works, it means the more likely you are to be able to find useful bugs. Something else to consider is that you're not just looking for any bug. If you're finding something that you could never reach from an attacker, it's just a bug in the program, it's not useful. So you want to make sure that when you're spending your time doing the reversing, you're looking at stuff that would be potentially a security issue. So identifying kind of what code you can reach is an important part of it. And so how do you gain this knowledge about kind of any large system? A bunch of different ways depending on what the system is, but looking for any kind of public documentation that's out there kind of before you start digging into it. There's lots of, depending on what it is, there might be a lot of public research that other people have done. I find it very, very useful to look also at vulnerabilities that have been reported in the past. It kind of gives you an idea of, first of all, what code paths can be hit, and also what might be problem areas in the code. You don't want to limit, though, your search just to those areas. If there was 5 bugs in one area, it might mean the rest of the code is bad too, not just that one piece, and other people might not have looked elsewhere. So don't limit yourself to only areas that have had past bugs. Right, so large systems, where to start? So this is like when we're talking about something that's too complicated for where you could just start, at the entry point and start reverse engineering the whole thing. That you could do that with smaller programs, but definitely not, when you're talking about hundreds of megabytes of code. Yeah, and so Tim's talk yesterday afternoon touched on this a bit, but looking for places that are interesting to start looking at. So you kind of use what's available to try and get hints. If you have symbols, which you do in Windows for almost everything, that's a great place to start. You can also use logging strings to try and get information about what the functions might do. And your goal here is just to find an idea of a few candidate places to start looking at. And you want to slowly kind of grow your understanding of how these fit into the larger picture of how the system works. One good approach is like combining the static and dynamic analysis. And so you could throw breakpoints in a debugger and start seeing kind of what code you can reach. For example, like maybe found a function that looks interesting, but doing static analysis, is being called through a function table, and I can't see how to reference it. So one way to approach that would just be to put breakpoints on all the functions in that same table, and then just start fuzzing input and seeing if anything hits. And once you have a code path, that gets you close, it should be pretty easy to figure out how to get to the function that you're interested in. And so the last point there, so doing vulnerability research, it's a lot about being wrong and not finding anything. You do have to be a bit stubborn. So don't be afraid to make like the wrong guess and go look, down dead ends. If it turns out that you don't see anything interesting there, just drop it and move on to something else. Don't give up. Okay, some general bug hunting tips. Just wanted to share. Some of this might be pretty basic, but yeah, just in case. So yeah, you can only keep so much information, in the cache. Keep flushing it regularly, so keep notes. One of the things that's a big advantage or I've seen bug hunters who've been successful, is they're able to keep a lot of context about how the system works kind of in their head at the same time. So you can be like, oh, well, this function, I know it didn't handle this variable properly or didn't validate it properly, and then it was used over here, and I still remember that. But you can only remember so much, so having notes is super helpful, especially if you want to come back later. You can, instead of having to do the analysis all over again, you can just kind of refresh your mind about what, some interesting points. So keeping notes on things like any interesting behaviors or if arguments are not validated properly. In the past, I've been able to come back through, do multiple passes on code that I've looked at and find bugs that I missed the first time around with the help of notes. So it's definitely worthwhile reviewing your notes and maybe reanalyzing some of the code. Yeah, just wanted to make a quick note on some of the tools I was using for this particular project. So using whatever disassembler you want. In my case, I was using Ghidra, and just wanted to highlight that if you're doing something where there is source code available, like header structures, make sure you're loading any of those into the disassembler ahead of time. So in this case, the Windows uses the driver development kit. So you have a lot of structures, information you can load in, and that really helps doing the reverse engineering. Yeah, various ways you could load it. You could either load individual structures that you were interested in, or there's some like projects on GitHub for Ghidra specifically to help load all the import all the kernel structures. And then, yeah, Winbag, Scapy to make packets, and then Wireshark to make sure I was making the expected packets. Okay, so let's move on to some of the Windows internal stuff. So there's a fair amount of public knowledge about this. We're going to try and like distill things down to the bits that I found important while doing this research. So this is just a very basic layout of the network stack. So 2 years ago, I did a bit more vulnerability research, but looking at the stack from the top down. So I was looking for privilege elevations from user mode, and I presented about that previously, and there's a write-up on that available online if you're interested. But this time, I was looking up from the other end. So if you're getting packets off the network, how are they processed, coming up the stack? So here they come in at the bottom through the NDIS driver from whatever network card is being used, and then go through the different protocol layers in TCP/IP.sys. And at the top, you have, in the middle is AFD, which is the main interface into user mode sockets. And then you have TDI and TDX and WSK, which are both interfaces for kernel drivers that want to use networking, like socket programming. And where TDI and TDX are the legacy interfaces, and WSK is the newer one. So again, these are just kind of like the basic pieces of the networking stack. In addition, another key piece is the Windows filtering platform. So you maybe can't read that, but can sort of see what it is. This is also all from the MSDN documentation, so it's on there. And so this is where I'd actually kind of come into the research. Was this WFP is where you're supposed to be hooking in to get access to network data if you're like a third-party security driver. So I was working on development in kind of this code area, and then I got sidetracked into looking for bugs. And so the Windows filtering platform is fairly complex. Up in user mode, you have this big box in the middle is the base filtering engine, or BFE. And this is where user mode clients register with this. So you can have user mode clients up here, and also any kernel mode clients down here. And they interact with the BFE over RPC, which has some interesting issues during boot up or in other times when the kernel driver has to issue RPC calls to user mode. And if the service isn't responding, it can cause problems. It's fun stuff. And then if you're a kernel mode client, you are able to access the actual packet data as it's coming in. And so the clients down here, they register with the WFP, and then on this side over here, this is the TCP/IP stack, and there's various layers where they can get access to the network data. And when they're, they can either get just notifications that a packet came through, or they can actually intercept the packet and do any sort of modifications if they want to just inspect the data or modify it or queue it off for later processing or just inject new stuff. They can do whatever. And all of the callouts come with the ability to register filters on them. So from a performance point of view, you don't want all these drivers looking at every packet if they don't need to. So you can put filters on it to say I only care about this specific type of packet, and it should help with performance. Also in this diagram, if you can read it, I don't know, there's a few spots here where IPsec is referenced. So IPsec is partially implemented as a WFP client, which is this one at the bottom. That's where they do all the processing of IPsec packets and unwrapping them. There's some bits that aren't strictly WFP. There's a little bit of header parsing over here, and then a lot of the handshaking happens up in user mode. So just trying to show like a bit of the rough architecture and complexity involved in the kernel. Also, when I was at this point, I was curious about what other things are hooking into the Windows filtering platform callout table. And so this list was just, I was able to find the table and dump all the registered handlers. So this is just from a base install VM. And this, I kind of summarized the list of handlers that are registered. So at the top, you can see there's all these, the IPsec filters at the different layers. And then some various other stuff in TCP/IP. And then at the bottom here, there's a few other drivers that also register. This MPS DRV is the Microsoft Protection Service, which I believe is the firewall. NDU is for tracking network data usage. And this last one here, WDNIS, is the Windows Defender Network Inspection Driver. So these are just ones that are registered through the WFP callouts. However, these are not the only drivers that are do network processing. So this list of drivers, again, just trying to show like kind of the complexity of the system here. I found these by dumping all the imports for all the drivers on a stock Windows 11 VM. And these are all ones that imported the NDIS functions to access network packet data directly. So not just any NDIS functions, but only ones that would be accessing packet data. And while doing this research, the only ones I looked at were TCP/IP.sys and netio.sys. So, again, just highlighting, there's like potentially big other hunting ground for looking for other bugs. All right. So I mentioned a few slides ago that when I started this research, I was interested in following the path of packets coming into the system. Yeah, this was a good time to combine kind of the static and dynamic approaches. Looking at symbols, it was relatively easy to find things like the TCP receive function, but it's all through different callout tables. And looking at this in Ghidra, the call graphs were very short. It was like 1 or 2 functions and then going through a function table. But I was just put breakpoints on those and could get the full call stacks. And then using that was able to walk back up, find these function tables, and then also look for similar ones. So from just, breakpointing on the TCP receive, I could find the tables for the raw clients and UDP clients. So just going over this, which was much faster. You could have done it all statically as well, but I think this was much faster. Right, so data comes in off the network card. It goes into the protocol layer. Does any IP-specific handling, including fragmentation. A lot of that happens in here. And then there's what, based on the symbol names, are called like a protocol demux table. And so that forks it off, and ICMP processing or IGMP, IPsec is in there. And there's individual tables for the different, some of the different IPv6 options are all handled through this protocol demux. And then depending on what packet type it is, if there's, if it was just decrypting it, or it was unfragmenting it, it'll get sent up into this transport dispatch table. So at this point, any packets would have been reassembled, and they're ready to be sent up to the higher layer. And in this case, there was 3 different clients, which roughly correspond to the different socket types that Windows uses. So raw clients, TCP clients, and UDP clients. And there was function tables for all those to handle the different socket operations. And on here, I can also point out where the various Windows filtering platform inspection points are. So the lowest one is at the IP layer, where you'd get the raw IP packets, same as they came in off the network. And then there's a transport layer where you would get them after they'd been assembled together. And there's also layers for ALE connections, which is when a socket connection is made. So whether it's a TCP connection is established or a UDP connection is. And then also at the stream layer, so you can say, I just want to see the TCP data or UDP data, and you can also register for that. So something else to cover that will come up later is some of the key structures, or this key structure, that's used a lot in the network stack. So the net buffer structures are used to access packet data as it goes through the stack. These 3 structure definitions are all available in MSDN, but the one we really care about is this one on the right here. Kind of key fields. It has the amount of data, the current offset into the packet, and then a chain of MDLs. And MDLs is a memory descriptor list, is what the acronym stands for, and it's just a way that Windows internally represents data. And we'll talk more about that on the next slide. So this is just a visual diagram of the different structure fields and how they apply to the MDL chain. So you can think of the MDLs just as individual memory buffers, kind of joined together into one kind of contiguous view of data. So we have here the data offset just points to where we are in processing the packet. So if we're processing a network packet and you go through the different protocol layers, you kind of think about this as each one is stripping off its headers. So instead of copying memory or doing anything else, you just move the offset of where you are and point to your payload, your data, and then hand it off to the next section. And then the data length is whatever is remaining in the buffer. What else did I want to point out here? Right. So there's functions also where the different protocol layers can change this offset. They can either advance the offset after they finish processing a header, or they can retreat it and go backwards. And maybe they're going backwards because they want to see some value in the header from the protocol before them. And for things so the big goal of these structures, of the net buffer structures, is for performance. and to minimize kind of the copying of data. So if you think about the IP fragmentation case, you'd have a bunch of small packets received, and then instead of, when they're reassembled, instead of doing a memcopy to copy them all to one single buffer, the idea here is we can just link them together in the right order. So when it's reassembled, there's one net buffer structure that just contains a link of these linked list of these packets, and so there's no copying required. And anybody accessing this data is supposed to use the helper functions to make sure you're getting contiguous data out of this. And with that, we'll go on to the function that does that for you. So this endless get data buffer, the idea is you just say, give me a pointer to the actual data in the packet. So you have the net buffer structure and you want a pointer to the data out on the other end. And you tell it how many bytes that you want. So those are the first two parameters. And if there's no fragmentation, if it's all like in contiguous memory, you just get a pointer back. That's all, no copying, nothing happens. But if there was a fragmented packet, or for some reason you were trying to copy over an MDL boundary, it will fail and return null. So in that case, if you need to handle that case, you just pass in a bit of storage. So the common pattern is either you just need a small amount of data, so you'd pass in a fixed size buffer, or if you might want a big chunk of contiguous data, you'd call it once to see if you could get it, and then if not, you'd allocate and do a copy. So if it is not contiguous, this function is essentially, it's just memcopy. Is how to think of it. Right, and the other functions are that I wanted to mention are this endless advanced buffer start. So I was saying before you could change the offset of where you're processing inside the MDL list. And so that's what this is. You just pass it the net buffer and the amount of bytes you want to go forward. There's a matching retreat one. And the advanced one, as you advance the data forward, if you knew you were not going to touch the data you'd processed already, you can set it to free any MDLs as you go. So maybe you don't care about the lower layer headers anymore. And the retreat function also has a flag where you can say, if you want to retreat and you're already at the beginning, it will just allocate empty data for you. I don't really know what the point of that is, but that's what it's documented as doing. Interesting. Okay, so just to repeat what I said earlier, I think looking into past CVEs is useful, so you can try and repeat the mistakes of the past. So in this list here, I only look back about 10 years. There were some older CVEs, but there was a redesign of the Windows networking stack with Windows Vista. So anything before that is less relevant. And there was a couple that came out right when Vista was released, I think. But I think there was a lot of bugs in Vista. Anyway, I didn't include those in this list. And so I'm just trying to show, like, I was trying to categorize, group the bugs to look for things that were common. So highlighting here the different columns, like which ones are denial of service versus remote code execution, which ones involve stack corruption or heap corruption, and which ones involve any sort of IP fragmentation. And so if you've been paying attention, you might have noticed that I've been mentioning fragmentation a lot. Yeah, there's a reason for that. We'll get to that later. So something else interesting about these is that as far as I'm aware, there's never been any published example of someone getting code execution from these. All of the proof of concepts are denial of services. No one's actually demonstrated getting code execution from any of these bugs. So remote kind of execution over the network is very hard. So either it was not possible with these bugs, or whoever did manage to do it decided not to share the proof of concept publicly for whatever reason. I mean, there's, yeah, I guess arguments about whether you should share remote network exploits, whether that's a good thing or a bad thing. I think people may have different opinions. Okay, so I'll just briefly go into a couple of the remote execution ones to look at just a few details about how they worked. So this one was from 2020. It's in an ICMP v6 packet handling router advertisements. And so the way this function worked is there was two loops in the function. The starting loop went through and validated the entire packet. And as you hit each option, there's like a length field, and it knew to jump to the next one. And then there was a second loop that went through and processed each of the options. But for one of the option types, and I assume it was this recursive DNS server option, it calculated the length differently for the option in the validation loop and the actual processing loop. So when it validated it, it was using the correct length. In the processing, if you formatted the option just right, it had the wrong length, and then the next option it went to process was like misaligned and it hadn't actually been validated. So what that led to was this call here, where we have this end-this get data buffer. And the option length here, and this is the only one that doesn't involve fragmentation. So because we bypassed validation, this option length wasn't validated, and it's a straightforward Stack Overflow mem copy onto the stack. Yeah, highlights potential problems with this data buffer, get data buffer function. So the next two here, they're kind of similar, and they're both in fragment reassembly. So both there's one in the IPv4 reassemble function and a similar one in the IPv6 function. So they're not the same. They weren't the exact same bug, but the same type. Essentially, if you have fragments, each fragment is going to have an IP header on the packet, and there was a bit of confusion about which copy to look at for data. So if you send different values in the IP header for the different fragments, you'd hit these two bugs. In the 74 was the IPv4 bug, and that leads to an out of bounds write. And the other one was the IPv6 version, and that led to a use after free bug. Yeah, so another fragmentation problem. And on the right here, I have the links, which I have in the references section at the end, but of the write-ups that I was using to look at these. You could, if there weren't write-ups available, I guess you could go through and do the patch analysis on each of the vulnerabilities, but that's a lot more work than just reading someone else's write-up, which are, in these cases, were all really good. Yeah, so this was from last year. This was the evil ESP bug. So this was dealing with IPsec and fragmentation. So there were bugs in two locations here that, when combined, kind of led to memory corruption. Essentially, it involves sending IPv6 options that were out of order according to the spec. So there was nothing in the code to stop you sending options, but it did say in the spec you shouldn't send them in that order. And if you didn't listen to the spec, then you could get this memory corruption. And so the end result was that you could get this next header offset to point past one of the end of these fragments and get a single byte of memory corruption out of this. And all of these papers, which I'll link to, I thought were quite good, worth reading if you're interested in that kind of stuff. Okay, so I want to now walk through like the path that I followed to find this particular bug. I'm not going to detail all of the dead ends I went down. So it may look easy, but yeah, there's a lot, probably most of the time was spent looking at stuff that turned out not to be interesting. Yeah, it's funny when someone tells you where the bug is and exactly how to get to it, it's like, oh, I could do that, it's easy. So, like I was saying before, like one of the ways to look for places to start is to dump symbols and then look for anything that potentially seems interesting. So obviously, the bottom table here already established that fragmentation could be interesting. And one of the other things I tend to look at is also error code paths. So often the error code paths are not hit that often, sometimes never. So there might be code in there that's not been looked at or not executed very much. And the functions I've highlighted in here, they're all different ones that look to be like they'd be processing receiving data. So like receive fragment, handle error, echo and reply. And this classify function down here, it implies that it's related to the WFP, Windows filtering platform, somehow, like the inspection points where you register to see packet data, they're called classify functions. So I assumed that was WFP related. All right, so just a quick overview on ICMP error packets. yeah, this should be pretty basic to most people. So it's just a standard IP header that's next protocol is ICMP. In the ICMP header, you'd have a type that specifies this is an error packet instead of just the echo request and reply. And then the body of the ICMP message typically contains the data for the packet that caused the error. So there's another packet in the body of this message, which would contain its own IP header and then however much of the payload is in there. In this case, it says like 8 bytes, but you can put an arbitrary amount of data in the payload. So this is kind of leading to this function, which was one of the ones I looked at. Again, definitely not the first. Yeah, quick aside, all of the code I'm showing is all from Ghidra's decompiled view, or it's not from, yeah, it's originated from Ghidra's decompiled view, but I've heavily edited it and reworked it to make it a little more readable on these slides. And so what I think this function is doing is it's trying to get the details of the inner packet that caused the error and send them off to one of the WFP clients through this function here. The WFP inspect seems to be where the point where any packets might go through the client processing. So what this code is doing is it's getting the IP header here, and it wants to look at it to figure out whether it should send it down the IPv4 or IPv6 code path. So it's looking at the inner IP header. And so started tracing down, and I would have traced into like all of these functions when doing the analysis, but again, we're only going to look at the interesting code path. So now in this skip headers function here, yeah, we'll walk through what this is doing. So this very first call here is just trying to get the basic IP header, IPv4 header, which is in hex 14 bytes. And then once it has the basic header, and it provides a local storage buffer that is big enough, so there's 14 matches there and there. And once it has the header, it can then look at the length byte, or length field to see how big the actual header is. And then in this side of the loop, it validates, okay, we do have enough data for the inner header, and it's checking if the header length is not the default 14 bytes, then there must be options in it. So it skips over this advanced net buffer, moves the pointer up past the IP header to where the options are, and then calls into this options helper. So at this point, there's no bugs in this function here. It's just moved the offset right up to the beginning of the options field. But then if you go down further into this process options helper, you can see here now they're starting to access the data, but they're not using that get net buffer data function. So they're just getting the raw pointer out of the MDL and adding on the offset. So guaranteed to have at least 1 byte here, but after that there could be, if there was a fragment right after this packet data, they wouldn't have the whole options field. So I think at this point, this function was probably written assuming that they were dealing with just the original, like the outer IP header, because you're not allowed to fragment an IP header. So you can't, like there's multiple places where it's checked earlier on. You can't send a IP header with the fragments. I think the network cards will drop it entirely. So they were probably assuming writing this that there's no way you could have a fragment boundary inside an IP header. And then once it has the pointer to the data, it just starts walking through all the options. Options are just standard type length value fields, and bumping up the pointer by the option length. So yeah, I got to here and I was like, well, this for sure looks promising. If the buffers are fragmented, I'm pretty sure this should just read right off the end of the buffer. But I'm always pretty skeptical until I see a crash. I think there's been way more times where I was convinced I'd found a bug and I was wrong than the times I've been right. So I tried not to get too excited at this point. And so the next question is, okay, have found an interesting function. Looks like it does something bad. So where can we reach this from? And it was easy. There was one reference to the code from this Windows filtering platform function, and it sounds like it's processing any transport data. So this is transport. The transport layer was, again, after any IP fragments had been reassembled or IPsec encryption had been stripped off. This callout would happen. So it seemed like, yeah, we could definitely hit this. And I could get a breakpoint on this function really easily. But then when I got down to the block where the error classify function was being called, there was this check on a flag, and it wasn't passing. So that flag was not being set. And so if this was source code, it would be really easy. I would have a name for the flag, and I could just search and say, where is this flag set? But here, like, I don't have any info. I know it's a void pointer. It's some sort of structure, but don't know anything else yet. So how do we make sense of this data? So dealing with whether it's Ghidra or IDA or whatever, you can auto-create structures, and this is typically the output that you'd get. You'd get some fields that it would figure out roughly what they were, but give you really helpful names like field 2FC. So how do we kind of enrich that to get more details? So one of the tricks for Windows is if it's a piece of allocated memory, Windows is pretty verbose about their pool tagging. So for any allocation, you can say, give me the pool that this is from, and it will give you the allocation size and the tag, which is like a 4-byte value for what this allocation is. And then really helpfully, they also include like descriptions of what all the tags are. So I looked at this particular tag, and this was the pointer to arg0 in this case is what I was looking at. And it says, oh, it's an ALE endpoint context. And ALE basically corresponds to the socket, so it means it's a connection for either a UDP socket or raw socket, whatever the type is. And so that gave me a hint that, okay, well, at least I could like name the variable now. I know it's like an ALE endpoint. It seems like it makes sense. But was also able to then start searching for related functions. So just searched for symbols that had the name ALE endpoint in it, and there was a creation handler, and often like structure initialization is pretty simple, but it might give you more hints. So in this case, I was able to reverse engineer that function and get more details about what the different fields of the ALE endpoint structure were, and also find other places they were used. So I probably could have guessed it was a flags field without doing all of this, but after finding that create function, I was actually able to go and figure out where the flag was being set. And it turns out if you have a raw socket, then that flag is set. So yeah, that seemed easy. I'm like, now I think I have a bug, and I think I know how to call it. So creating a raw socket, listening on the system, and then I was able to hit this code path. So it was time to figure out, okay, now what do I actually want to send? And so this was what I had in my head. I want to send just this packet that has the standard IP header, and again, that outer one is not fragmentable. Anything after that you can fragment, but not that outer header. And then stick on an ICMP header, reporting some sort of error, and then the body of the ICMP packet would be another packet. In this case, I'm going to send an ICMP ping in here. But this time, with the IP header, I'm going to add on options, which are here in blue. And then the goal is to send this where it's fragmented right in the middle of these options and see if we can get a read past the end of the buffer. So it's like pingception here, which led to the whole like point of the talk was to try and get this slide in here. That's where the name comes from. This is a clip from Hunt for Red October. One ping only, but we're sending sort of two. So I did a really quick focus group last night to see if I should try and do my best Sean Connery accent. Verdict was no, so sorry. Right, so the proof of concept script, super simple. This is using Scapy to build a packet, fragment it, and send it. So we have our ICMP error type here. We build an IP packet body with just some options. I don't even remember what this type is, but it doesn't matter, it just needs options. And then the body is an ICMP ping packet with the fragment size chosen to be quite small so that the boundary of the fragment should be through the options field. Yeah, and then this is a little video. I posted this right after the bug got patched online, so some of you may have seen it. But yeah, just starting a raw socket listener on the target, and then running the little proof of concept script to try and trigger the bug. Has to run a few times because it only crashes if you happen to get past the end of a page of that's not mapped. Yeah, often you just read from a page. Thank you. Now, if I keep playing it, will you keep clapping? So yeah, when the bulletin came out, they actually included more details than I expected in there, and they said that raw sockets were required to hit this bug. But it turns out there's a lot of code paths to this skip network header function, and not all of them come through that one classify, ICMP error classify, which that one required raw sockets. And so I was able to hit the bug over, you can see, or maybe you can see in here. These are IPsec functions. So I was able to set up an IPsec tunnel and send a ping error packet through that, and was able to trigger the bug that way. But it's way easier just to open up a raw socket than to set up IPsec. So you may have read the talk description, or if you're following closely, I kind of even said at the beginning I was going to talk about a remote code execution bug. And this bug got a critical rating, but all I've shown so far is an out of bounds read leading to a denial of service. So what's going on here? This is the CVE that the bug was reported under, or was given. And the original bug report was just a denial of service. And so about 2 months after I got the initial confirmation that yes, Microsoft thought it was a bug and they'd confirmed it, I got another note saying, oh, by the way, we've upgraded this to remote code execution and given it a critical rating. So I was like, well, are they either being super conservative, right, or about their classification of the bug, or is there something else going on here? Well, and I knew there was something else. Well, I'll get to that. Anyway, so if we go back to this skip network layers function, there's this third parameter that I've circled there into the process options helper. In this code path, it's set to null. And then where the actual bug was in process options helper, which is where the options can be fragmented. If we look a little further down in the function when it's processing the options, if there's timestamp options and that context pointer is not null, then it goes and does something with the timestamp option. So I was like, well, okay, two questions. What is that pointer and what are timestamp options? I'm not going to show the disassembly of the process timestamp option function because it's pretty simple. But essentially, the idea is that these options are used to give the time when a packet was processed by any hop in the receive path. So if there is one of those options, the receiving endpoint is supposed to write the current timestamp. So that's all that function does if we go back, is if there is a timestamp option, it looks into the buffer and writes the current timestamp. So in this case, if we were fragmented, it will go and write the timestamp beyond the end of the buffer, which is interesting. So yeah, I looked for ways to get to this. So there's a couple different tables in the kernel that are used for handling the IPv4, v6 abstraction. There's these global tables, and in there they have various function handlers. One of them is to validate any network buffers that come in at the IP layer. So they want to validate the IP header, and it comes through this function call, validate net buffer, then process options, and then the one we want to get to, which is the process options helper. And this code path has that receive context pointer set. So if we could ever get to this code path with a fragmented header, then we could potentially get remote code execution. So I was aware of this before reporting the bug, and I spent a lot of time trying to find a code path prior to reporting, because knowing, that remote code execution is much cooler than denial of service. So, but and my main guess for this was that if you did something like try to deliver a packet through IPsec, like I was able to do with just the ping packet, you could maybe have some fragmentation issues. But yeah, like I mentioned before, IPsec is not simple to set up, and there's a ton of options. You can have the different versions of the key exchange. There's authentication headers versus the encapsulating headers. You can have both transport mode, tunnel mode, main mode, aggressive mode. And so I was able to set up a few combinations of it, but definitely not exhaustive at all. And everything I tried, I couldn't get there were some validation checks, or I couldn't get the packets through to hit this this particular code path. There's also other VPN implementations. So pretty much anything in the kernel that wants to do any like decryption, or I'm not sure what else they'd be doing, but you can receive packets, process them, and then re-inject them into the bottom of the IP stack. And if you could get something through there that was fragmented, you could potentially hit the bug. But it's kind of a downer. I didn't find anything. But my guess is that Microsoft did, or they wouldn't have changed the rating on this bug. So maybe with like full source code access, you could find some way in. Sadly, I don't think most of us have that. Okay, so if you could actually get a code path to hit this bug, how would you actually exploit this, or could you actually exploit this? So, yeah, we have a pretty basic out of bounds write with a few constraints. So we do control a few things. We control the allocation size. It's relatively small, but we do have some flexibility over where we're going to draw the line for the fragmentation. So how big those fragment buffers are going to be. And we can control the overwrite offset, so how far beyond the end of the buffer the write happens. But what we don't control is the contents. The timestamp's going to be written, and we also don't control the length. It's just a 4-byte length, I think, that gets written. So I have seen other remote bugs get exploited with less control than this, but I think this would definitely not be trivial. And given that I couldn't find a path to hit this, I didn't bother trying to see if it could be exploited. Yeah, so just about there. So my conclusions from all that, computers are hard, but reverse engineering and bug hunting is fun, so still a good project. Yeah, these are the few references for the blog posts for the different CVEs I was looking at. And that's it. Yeah.